Hello, welcome to our Semiconductor education program. I'm Vincent Chang. In this video, BJT Differential Pair Part 2. So I'm going to present the three modes of operation of the differential pair. Here's the circuit, the differential BJT differential pair to match the BJT, to match the collector resistance, and the external large signal VB1, VB2, and transistor are biased by a constant current source, which is pulled down to the negative voltage. On the top is a positive supply voltage VCC, differential pair circuit. Transfer characteristic. If we define the difference between the large signal VB1 and VB2, again, the subscript is capital, okay? If the subscript is lowercase, it means the small signal. So the subscript now is the capital D. It means it represents a large signal differential voltage. And in the previous video, Part 1, and this has been solved. The two current in terms of with respect to the input differential voltage normalized by the thermal voltage 25 millivolt. So IE1, IE2 in terms of the large signal differential input VD. First mode of our operation is called common mode. It's called common mode. So common mode input, which means the two inputs are tied together and connect to a common mode, common voltage, a common mode input voltage. V denoted by the VCM. Okay, pay attention to now the two input voltage input signal has been connected, tied together, and connect to a common voltage, a common mode voltage. So in this case, if I ask you by instinct, so what is your instinct answer for this? 50-50, right? Because it's symmetric. It's a symmetry. You have VCM on the left. I also have the VCM on the right. So symmetry. So common base voltage, common emitter voltage, same VB. So there's no reason that the current will be split in a different way, split differently. Should be 50-50, half-half. So total is IQ. So 50% of the IQ go to the left-hand side, the other half on the right. And IC equals alpha IE. Why? Because assume the transistor has been operated in forward active region. IC equals alpha IE. If you look at the transfer characteristic, when VB1 equals VCM, VB2 equals VCM as well, then the difference is 0. So when difference is 0, VD is 0, which means the circuit operates in the red point. Is located on the red point. So red point at the red point, for this reason, as a result, the IQ split 50-50, IQ divided by 2, half IQ. You get the collector current, then we can have the collector voltage on the two collector terminal. So VC1 equals VCC minus the voltage drop across RC. VC2 is the same. Common mode. So common mode, you have the common mode, right? So if we just imagine this, if we put the VCM equals 1 volt, here's the result. Then you change the VCM from 1 volt to 2 volt, the result is the same. 2 volt to 3 volt, same. And 3 to 2, same. 2 to -1, as long as the transistors are biased in the active region, that means the result won't change. Then what does that mean? That means the circuit kind of no response to any common mode input voltage change. It even reject the external common mode voltage. So this phenomenon is also called the common mode rejection. Common mode rejection. The system has no response. Reject the external common mode input voltage. So common, that's how the name comes from. The common mode rejection. The second mode, switch mode, the current switch mode. Let's say if you have the difference, a large differential input, 0.5 volt. The right-hand side, the base of the right-hand side is connected to the ground. The base of the left-hand side is connected to the 0.5 volt. So the difference is 0.5 volt. What's the result? If you solve this by instinct, then negative 0.2. Because it's large, right? So it's going to drive the left-hand side transistor. So down to negative 0.2. So the voltage across the emitter base junction of the right-hand side transistor, Q2, is only 0.2. 0.2 is too small. So the Q2 is off. Then Q1 is on. Therefore, the current is going to go through the left-hand side like this, while the right-hand side is cut off, no current. In other words, the current, the constant current is going to switch to the left-hand side. Right-hand side has no operation. Current is going to switch, so current switch mode. If you look at the transfer characteristic, 0.5 is actually, I said this, I didn't know. I'm not sure if you listened carefully 2 minutes ago when I said 0.5 volt is large. Large. How large? Remember, the horizontal is normalized by the thermal voltage. So how big is the thermal voltage? 0.025. So it's the 20 times. It's the 20 times of the thermal voltage. So in this graph on the left-hand side, 4, this is 4. 4 and 8, 12, 16, 20. So it's here. It's out of the, it's here. It's here. From the transfer characteristic, it tells us in this large, the Z zone, the IE1 will be IQ, IE2 will be 0. So IQ 0, alpha IQ 0. You can get the left-hand side, the voltage is down, while the right-hand side is connected to. I don't know if you heard the circuit in the digital integrated circuit called the emitter couple logic, ECL. Or you can just pause and Google the Google ECL. The emitter couple logic is the digital circuit. So digital circuit, the ECL is operated in this mode of operation. So when the current switch on the left-hand side, this output down is the low, logic 0, while the right-hand side is connected to the high voltage. Okay, low, high, 0, 1. If the current gonna switch on the right-hand side, it flip, becomes the left-hand side terminal connect to the high voltage, and right-hand side terminal collector voltage is gonna down to 0. Logic 1 and logic 0. I just want you to know the emitter, the famous emitter couple logic, use the differential pair in the current switching mode. It's operated this way. Let me just go a little bit deeper by using the simulation result. This is the result from the SPICE simulation, the transfer characteristic. You see this big X. So I want you to get a little bit more familiar with, get a little bit sense about the what is big, what is small. You see 979.84, which means 22%, 98%. How much? 100 millivolt, 4 VT. So if the difference, now you got a sense, if the difference is the 4 VT, then 295. 98, 2%. So 298. What about 99, 1%? 4.6. So 4 VT, 2 to 98. 4.6 VT, 1 to 99. 1 to 99. Small signal operation, the third type of mode for mode of operation is called small signal. For the small signal operation, I'm going to teach you more in depth about how to analyze the small signal, do the small signal analysis in the upcoming video series. But I just want to point out one concept. Where the small signal operation operate in the transfer characteristic. First, it's bias on the common mode. And then move around. If you oscillate, if you just imagine, if we have the small signal, right? If the VD now is the small signal input, then you put the small signal on the horizontal axis. How the blue one will respond? It go like this way, right? Up, down, up, down. How about the green one? Because the slope is negative. It's going to down, up, down, up. So I just want you to get the sense the two AC currents should be what? Should be out of phase. Should be out of phase. So the small signal operation for the differential amplifier is going to operate around the red zone within very small linear range. Small signal operation in the red zone. The very small, narrow linear range. Takeaway. 3 modes of operation. First, common mode. Common mode rejection. The circuit has no response, even reject the external output signal. The second mode is called current switching mode. If VB1 is larger than VB2, much greater than VB2, then current switching on the left-hand side. If go the opposite, VB2 is much greater than the VB1, the current go to the right-hand side. Current switching mode. The third one, small signal operation, is centered around the common mode and operate within a very small linear range. This is where the small signal differential amplifier operates. We have come to the end of the lecture video. Thanks for watching.